Hi guys, Professor Burns here. We're going to take a look at section 3.4, which is on complex eigenvalues. So we're getting a little bit more into some special cases of what happens when we solve for our eigenvalues and we end up with complex numbers. So the first thing I want to remind you about, and I say remind, I think you probably saw Euler's formula at some point, maybe in Calc 2. I think even in History of Math, you guys might have mentioned it. Or possibly even pre-calculus. And if you've never seen it, that's okay too. It's not that big of a deal. But basically, Euler's formula says that if you have e to the I theta, so I, of course, is the imaginary number I, theta is your argument or your angle, that can be expressed as cosine theta plus I sine of theta. So the I always goes with the sine term, cosine is always the real term. And a lot of times we'll shorten that up and just call it cis theta. So this thing right here, I would just read it as cis of theta. So cosine I sine theta, that's the idea. And so how does that apply to what we're doing now? If we have alpha plus beta I, let's suppose that that's our solution. So our eigenvalue is alpha plus beta I. Then we could expand that, and t, of course, is the angle. We could expand that by writing it as e to the alpha t times e to the beta it. So far, I'm just using exponent rules is all I'm doing. And that would get expanded as e to the alpha t times, because you've got this complex number here, you've got this imaginary number, cosine of beta t plus I sine of beta t, using Euler's formula. And then if you want to shorten that up, you can write it as e to the alpha t times cis of beta t. Since beta t then would be your argument. Sorry, my pen's acting funny. Here we go. So that would be beta t. So beta t would be the argument. So this will work even though we know there's two solutions when we have complex solutions, one with a positive and then its conjugate. But it doesn't matter. As long as we know one of them, we're good to go. So let's talk about how that applies to solving a system of equations where we get those complex eigenvalues. So we're going to start with this system. I'm going to start by finding the determinant of this matrix so that I can get my eigenvalues. So that would be negative 2 minus lambda squared minus a negative 9, so plus 9. We want to know where does that equal 0. So I'm going to move that 9 over. So I have negative 2 minus lambda squared equal to negative 9. Take the square root. I have negative 2 minus lambda equals plus or minus 3i. So then if we solve for lambda, we wind up with lambda is equal to negative 2 plus or minus 3i. So that means my alpha is going to be the negative 2. That's always going to be the real part. And the beta is just going to be 3. And that's always going to be the imaginary part. I'm going to go ahead and highlight that because I think we're going to need it again. And I just want it to kind of stand out. All right. And then where do we go from there? So our lambda value that we want to work with, now whether we call it lambda 1 or lambda 2, it really doesn't matter. We're just going to work with one of them, so it doesn't matter. So the lambda that we want to work with is going to be negative 2, I'm just going to use the positive, plus 3i. And so e to the lambda t becomes what? Since this is our lambda, we're going to have e to the negative 2 plus 3i t, and then using Euler's formula, that becomes e to the negative 2t cis of 3t. All right, so just like in the previous section, we're going to use this information to find our eigenvalue. So what that means is well, let me back up. Let me remind you, just as a refresher here, that to get that eigenvalue, I need to find, I'm going to take my coefficient matrix times my variable matrix, and that has to be equal to whatever lambda is times that variable matrix. So we need to find a scalar multiple that works for that. So in this case, that's going to be negative 2, negative 3, and then 3, negative 2 times x and y, and then my lambda was -2 plus 3i times xy. So let's go ahead and expand this and see what that gives us. So if we expand this, we get -2x minus 3y for that top row would equal to -2 plus 3i times x. And then you just got to be a little careful with your algebra here. Make sure this gets distributed. So we have -2x plus 3ix. And then just like always, you want to solve for y. Notice that those -2x's are going to go away, so we're left with -3y equals 3ix. And then if we divide by the -3, we end up with a straight line solution of y equals -ix. So that's what we're going to use to come up with our corresponding eigenvector. So the eigenvector that goes along with this is going to be, just like always, choose a value for x to start off. Try to pick something that makes the numbers not so bad to work with. I don't have any fractions here, so I'm just going to let x equal 1. And so if x is 1, that means my y value, my corresponding y value would be -I. And that's the eigenvector that we're going to use as part of our solution. So now let's put all of this together. And I apologize, a little messy. I didn't leave you enough space, so just do the best you can. I've gone ahead and bumped my screen down a little bit. Like I said, just try to squeeze in, do the best you can. But my particular solution then, using this eigenvector, is going to look like e to the -2 plus 3i t times the vector 1 -I. And then let's clean that up. Let's simplify that just a little bit. I'm going to use Euler's formula to write this. Remember, -2 is your alpha and 3 is your beta. So this could also be written as e to the -2t cis of 3t times the vector 1 -I. And then I'm going to expand this cis 3t using cosine plus I sine theta. So then this becomes e to the -2t times cosine of 3t plus I sine of 3t. And make sure you see what I'm doing here. This is simply, I'm just multiplying it through and I'm expanding it back out using the cosine plus I sine. So then the next term, notice there's a -I in front. So it's going to be -I cosine of 3t minus I squared times the sine of 3t. And then again, let's simplify this just a little bit. We get e to the -2t times, let's see, cosine of 3t plus I sine of 3t. And then down here, now I squared, of course, is -1, so negative makes that a positive. Watch how I write this. This turns into a real number, right? This is just going to be 1 because it's I squared and negative in front. So that means the sine of 3t term here is actually a real term, not an imaginary term. So I'm going to write that in front. I'm going to write sine of 3t minus I times the cosine of 3t. And sorry, that's so messy. Let me see if I can move that over just a little bit. Maybe a little bit. Okay, so that's sort of the expanded version. Let me write that parentheses again. And one thing to get the general solution, so here's kind of the grand finale. The general solution, we need to be able to simplify this and identify which part is the real part and which part is the imaginary part. So what I'm going to do then is I'm going to write my general solution as the real part first. So the real part is going to be e to the -2t times, now what are the real components from this expression? Well, cosine of 3t would be the x component, and sine of 3t will be the y component. I'm just, make sure you see where I'm getting that from. That's just these two terms right here. Those are the real parts. And then likewise, we have an imaginary part of our solution. So we've got an imaginary solution would be the second terms right here. And notice they both contain an I. So I'm going to go ahead and put the I in the front. So we have I e to the negative 2t, and then what's left, sine of 3t becomes the x component, and negative cosine of 3t becomes the y component. Now, why is it important to identify the real and the imaginary parts? Because when we write the general solution, this is how we're going to express it. All right, so our general solution is going to be expressed as k1 times e to the negative 2t cosine 3t sine of 3t, so that's the real part, plus k2 times e to the negative 2t sine of 3t negative cosine of 3t, and this is going to be the answer. A couple of comments about this. I know there's a lot, so just kind of hang in there. We'll definitely do practice with this tomorrow. But what I wanted to mention was when you write out the general solution, all you're really interested in is the real parts of your solution. So the real part of the solution, the imaginary part of the solution, all I'm interested in is the real part here, which is what this part of my solution is, and then the real part here. And what I want you to notice is I did not include the I in this part because that's not part of the general solution. All we want to include is what's real. All right, I know that's a lot of stuff. Like I said, we'll do some practice with this in class. Last thing I want to talk about is what these phase portraits look like for these eigenvalues when they're complex numbers. So a few different cases, and they're all based on the alpha, what the sign of the alpha is. So the first one is if alpha is negative. So remember negative lambda values previously, that meant that we had a sink. If they were both negative, everything went towards the origin, and so that's going to happen again. This time we're going to have what's called a spiral sink, and everything is going to go towards the origin. So the image would look something kind of like this. Actually kind of cool pictures, but everything kind of spirals because of the periodic nature of these solutions. Everything spirals towards the origin. And then over here, if alpha is positive, remember previously positive lambda values gave us a source, and so that's what's going to happen here. We're going to have a spiral source, which is going to look similar to the previous one, with one main difference, of course, and that's everything is going to go away from the origin. So my spiral would look similar, but this time my arrows are going to indicate my solution directions go this way. And then finally, if A equals 0, this one isn't very exciting. That is called a center, or also called a closed orbit. And it's literally just a point at the origin, and that's all it is. So last part, let's sketch the phase portrait for the previous example. So what was our alpha value in the previous example? Well, that was -2, so that means that we are going to be looking at a spiral sink. So my alpha value was -2, so I'm going to go ahead and draw just a real basic sketch here. Everything is going to be going towards the origin, and we would have some other solutions around it that kind of follow the same pattern. Let's quickly look at what this looks like in using technology. And here it is using GeoGebra, and this picture certainly is much nicer than the one that I had. It's not going to show us the eigenvectors because we're only looking at the real plane here. But notice that we do have complex eigenvalues. So there they are. You can see them. And what I want you to notice is that everything, we've got these cool looking spirals, everything is approaching the origin. And it's going in a counterclockwise direction, which we'll talk more about later on. All right, I think that's it. So make sure you bring your notes with you to class tomorrow, and we will definitely do some practice with this. So I'll see you then.